Bismillahirrahmanirrahim. Dear students, today we are going to discuss about Polonovski reaction, which is basically the formation of carbon-nitrogen bond. The ingredients used for this conversion include nitrogen oxide species, or you can say tertiary amine oxides, N oxide of tertiary amine. This substrate is treated with acyl halides or anhydride to get the amide and an aldehyde. The nature of the products can be varied, can be changed by changing some conditions or some mechanism, route of the reaction, by applying some specific reagents. That is, we can obtain from this reaction by using a set of conditions as amide and aldehyde, and we can also obtain from this reaction enamines, or we can also obtain alkenes. We can also convert this into an amine. So these different nature of products depend upon the conditions provided to these this reaction. So this is basically all about of the Polonovski reaction, which provides different a large number of nature of products, but today we will specifically discuss about the formation of amides and aldehydes, which is the basic Polonovski reaction, and we shall confine ourselves to this discussion only. The key points of today's lecture is number one, the introduction to Polonovski reaction, second, the overall mechanism with respect to anhydrides using specifically acetic anhydride, and then the mechanism with respect to acyl halides, discussing its two different ways of mechanism with respect to acyl halides, and then in the end the explanation of the mechanisms step by step. In 1927, Polonovski brothers, these were two brothers with a similar suffix of Polonovski, so therefore this reaction is also termed as Polonovski. So these brothers were working on the natural product chemistry, and they prepared an acetyl derivative of alkaloid by using alkaloid N oxide, and they moved towards the cleavage of alkyl groups, which was attached to this nitrogen, with which oxygen is also attached, and we are naming it as N oxide. They used acetic anhydride or acetyl chloride for this purpose, and after then a lot of work on this step, on this way of reaction, it was recommended best method for the demethylation of tertiary amines. Demethylation means the removal of methyl group from the nitrogen of a tertiary amine in very mild conditions through this reaction. This is mild condition is because the other methods available for the demethylation of tertiary amines require vigorous conditions as compared to this one. So this reaction was preferred for this step, for this process of demethylation of tertiary amines. First of all, the tertiary amines N oxides are taken, and they are activated by the use of acyl halides or anhydride, and this activation results into the formation of iminium ion intermediate. This iminium ion intermediate has stability which varies depending upon its formation, and in some cases it acts at the same time. As soon as it is formed, it is converted into the further steps. But in some cases, which is also termed as the modification of Polonovski reaction, we can convert this aminium ion into many other useful products depending upon the nature of the nucleophiles used for this purpose. Here you can see the overall reaction of this Polonovski. First, tertiary amine N oxide. N oxide, because oxygen is attached to nitrogen, is converted treated with acetic anhydride here using DCM as dichloromethane as a solvent along with pyridine, and you get an amide and an aldehyde. Here you can see the aldehyde, the alkyl group, which is converted into, which is present in the aldehydic functionality, is that one which is attached on the alpha carbon. That is the alpha carbon is you can see the basic requirement for this for the progress of this reaction. We shall discuss the mechanism, then you will see how this alpha carbon plays an important role in the formation of these products. So R2 group is coming from that group from which alpha carbon has been used for the progress of the reaction, and other two groups which were already attached to the nitrogen directly remains on the nitrogen, and we get amide and an aldehyde. Here is given the overall mechanism of this reaction. You can see that as we have discussed in the last slides, that we can use acetic anhydride or we can use acyl halides. So I am giving here the mechanism for the anhydride and also for the acyl halides, and also there are two cases in case of acyl halide. First we discuss about the mechanism with anhydride. Here you can see the N oxide of tertiary amine acting as a nucleophile through its oxygen, attacks on the carbonyl carbon of acetic anhydride. There are two carbonyl groups of anhydride, any one of can be used for this purpose, and you know that carbon is electrophilic center with partial positive charge and oxygen is electronegative center. So O minus oxide acting as a nucleophile attacks on this electrophilic carbon, making the oxygen breakage of double bond and making oxygen negative, and then this negative moves back towards the carbon, making again double bond, and the carbon oxygen bond is broken and we get the acetate ion along with the main addition product. So we get the here nitrogen with 4 bonds. So here also there are 4 bonds as was in the N oxide. So the positive charge in nitrogen remains as such, and the acetate ion now abstracts the proton from the alpha carbon. Alpha carbon means the direct carbon which is attached to this nitrogen of tertiary amine oxide. So this alpha hydrogen is abstracted, and the 2 electron, here you can see the acetate ion is coming with negative charge, so hydrogen will be abstracted as a proton H plus. The 2 electrons between carbon and hydrogen will be moved towards the nitrogen, making their double bond, and at the same time the nitrogen oxygen bond will be broken and we will get the acetate ion as a byproduct. And here we get the iminium ion formation. First step was the acylation of this N oxide tertiary amine, and second step after that attack of acetate ion on alpha hydrogen, we get the iminium ion after the elimination step, along with the formation of acetic acid. And acetate, this positive charge of nitrogen is counterbalanced by the acetate ion. First was also acetate ion, which was also used to obstructing the proton, and here with iminium ion, the positive charge is also balanced by the acetate ion. This acetate ion, acting as a nucleophile, again attacks on the alpha carbon, and double bond is moved towards the nitrogen, and we get a simple amine, tertiary amine, bearing the acetate group. And this we can say the alpha acetyloxy tertiary amine. Alpha because the acetyl group is attached at the alpha carbon. In the next case, there are two chances for the movement of the reaction. First chance is that acetic anhydride, another molecule of acetic anhydride, comes, and the nitrogen, whose lone pair is now available, free for the nucleophilic attack, which was not available when it was making 4 bonds. Now it is making 3 bonds. The lone pair of nitrogen is available, which attacks on the carbon, and as we have discussed in the first step, the double pi bond, carbon oxygen pi bond, is broken. Then it moves back in the reformation of double bond and the removal of the acetate ion, and we get again nitrogen with positive charge, which is counterbalanced by the acetate ion. In the next step, the counterbalancing acetate ion attacks as a nucleophile on this carbonyl carbon of acetyloxy group, and we get first step is similar as the last, that first pi bond will be broken first of carbon and oxygen will get the negative charge, and in the next step oxygen negative charge will move back towards the carbon, reforming the double bond, and the carbon oxygen bond is broken, and the 2 electrons are moving towards the next carbon oxygen bond, that is the alpha carbon with nitrogen, and oxygen will get a double bond. We will get here the byproduct of acetic anhydride, that is acetic anhydride which was used in the last step is reversed back. It means that it was acting as a catalyst here in this step. Next, when we get the carbon oxygen double bond, at the same time the carbon nitrogen bond, alpha carbon and the nitrogen bond is broken, and we get the nitrogen in trivalent state, that its positive charge is omitted, is finished, and now we get the 2 products. One is the amide, nitrogen is attached with the acetyl group which was provided in the last step by the acetic anhydride, so it is converted into an amide, and the R2 group now is attached with the carbonyl group, so it is converted into an aldehydic functionality. This was the one way of the formation of the product. The other way is the intramolecular cyclization. This was the intermolecular because 2 different molecules were interacting to form these products. But second is the intramolecular cyclization, intermolecular reaction, which moves into a cyclic intermediate and then into the product. Here you can see that the nitrogen, lone pair of nitrogen attacks on the acetyl carbon of acetyloxy group, which is attached on its alpha carbon, and oxygen gets the negative charge, and we get a cyclic 4-membered cyclic ring. Then when this minus negative charge moves back towards the carbon oxygen bond next move towards the carbon oxygen, alpha carbon and oxygen, and we get the double bond for the formation of aldehyde, and the alpha carbon nitrogen bond is broken, which moves towards the nitrogen, and we get the amide along with the aldehyde functionality. So this is overall mechanism with respect to anhydride. Here is another overall mechanism, but this is with respect to acyl halides. Here you can see acetyl chloride is used. First step is just similar to the last one, In that case, oxygen acting as a nucleophile attacks on the carbonyl carbon, and here is also the similar case, and we get the attachment of acetyl species on this oxygen of N oxide tertiary amine. Here the positive charge is counterbalanced by the negatively charged chloride ion. In the next step, this thing moves in cyclized form. Here you can see that the lone pair of oxygen of carbonyl attacks on the hydrogen. At the same time, carbon hydrogen bond is broken, which moves towards the carbon alpha carbon and nitrogen, and we get the double bond. And at the similar time, nitrogen oxygen bond is broken, and that moves towards the carbon oxygen single bond, making it double bond. That is regeneration of the carbonyl. And here you can see in the product side we get an acetic acid as a byproduct along with the formation of iminium ion, and the positive charge of iminium ion is counterbalanced by the chloride ion. In the next step, this formed acetic acid attacks through its oxygen, lone pair of its oxygen acting as a nucleophile on the alpha carbon, and there is a reattachment of this oxygen on the alpha carbon, and the carbon nitrogen double bond is converted into single bond. Now the oxygen gets the positive charge, so its positive charge is counterbalanced by the chloride ion. In the next step, this chloride ion removes the proton here in the form of HCl, and we get the simple alpha acetyloxy, derivative of that tertiary amine. Now second molecule of acetyl chloride again comes, and this time you can see the nitrogen lone pair of nitrogen acts as a nucleophile and attacks on the carbonyl carbon of acetyl group, and now acetyl group is attached to nitrogen directly, making it positive charge, and this positive charge is counterbalanced by the negative charge. In the next step, the negatively charged chloride ion acting as a nucleophile attacks on the alpha carbon, which is further attached to nitrogen and R3 group. Chloride ion is attached at this carbon, and the carbon nitrogen single bond is broken, and we get the simple amide formation along with the formation of byproduct. Here the byproduct is you can say acetyloxy alkyl halide, or you can say chloro, an ester having chloro as a substituent. After the hydrolysis of this product, we can get the aldehyde along with the formation of. Here you can see, if you see it keenly, you see the R3 group of aldehyde is coming from that carbon which is chloro 1. Chloro, that is R3 group bearing carbon is converted into the aldehyde, and the other carbon of acetyloxy group is converted into the acetic acid. You can see here it is simply an ester, and you know after the hydrolysis of an ester we get acetic acid and an alcohol. The acetic acid acetyl group is converted into the acetic acid and byproduct, and the other product is the alcohol, in which this chloro carbon bearing the chloro will bear the hydroxy group, that is this oxygen of ester is converted into hydroxy, and then after the removal of HCl from that product we shall get the aldehyde functionality, aldehyde product. So here along with amide and after the hydrolysis of this moiety we shall get aldehyde, and the byproducts will be acetic acid and HCl. So this is the overall mechanism with respect to acyl halides. Here is another way of reaction progress through acyl halides. The last discussed mechanism with acyl halide is little bit different from this one. Here the first step is just similar to the last step, that the oxygen acting as a nucleophile attacks on the carbonyl carbon of the acyl halides, and oxygen gets the negative charge after the breakage of pi bond. Then that negative charge moves back towards the carbon, making double bond, and halo group is removed with negative charge, and the positive charge of nitrogen tertiary oxide is counterbalanced by this negatively charged halo group. Now the difference is that from the last step, in the last step you saw that the alpha proton was obstructed by the oxygen of the acyl group which is attached to the nitrogen, but here in this case this proton has been obstructed through halo group, and the two electron between carbon and hydrogen is moved towards the carbon nitrogen, making it double bond, and acetyl groups is removed as a byproduct. The positive charge of nitrogen is counterbalanced by this acyl group, acylate group. Here we can get the iminium ion. In the next step, acetylate ion acting as a nucleophile attacks on the alpha carbon, and the double bond of carbon and nitrogen is broken, and nitrogen gets the trivalent state, and so its positive charge is removed, and we get alpha acyloxyamine. This step is similar to the last one. In the next step you see that the lone pair of nitrogen attacks on the carbonyl carbon of another acyl group, and this step is also similar to the last one, and we get the n-substituted acyl derivative. Here is the difference from the last step, that in the last step the halo group came and attacked on the alpha carbon which is attached to the nitrogen, positively charged nitrogen, but here in this case we are going to make the attack of this halo group on this carbonyl carbon of acetyloxy or acyloxy group, and oxygen gets the negative charge which moves back, and then in the next step you can see oxygen negative charge oxygen moves towards the carbon, making it double bond, and the carbon and oxygen single bond is broken, which is moves toward the alpha carbon and oxygen, and we get the double bond. At the same time alpha carbon and nitrogen bond is broken, and we get the aldehydes and amides along with the formation of acyl halide. So this is the overall mechanism. Here are some questions in the this second last step, when the halo group attacks on the carbonyl carbon of acetyloxy group. In the last step the halo group attacked on the alpha carbon. This thing looks to be better mechanism, better way of synthesis route of formation as compared to the last one, because the alpha carbon is not, although it is attached with the nitrogen, it is attached with the oxygen, but its electrophilic character is not too much high as that should be the that of carbons of these two carbonyl groups. One carbonyl group is attached to the oxygen and second carbonyl group is attached to the nitrogen. If you compare that, the alpha carbon is attached on one side from nitrogen and one side from oxygen, but in case of acetyloxy group the carbon is attached to two oxygens, and one oxygen is sp2 hybridized and one is sp3 hybridized. On the other hand, the other carbonyl carbon of amide functionality is in such a way that it is attached to two, one is nitrogen and one is oxygen, and also oxygen sp2 hybridized. So as compared to alpha carbon, these two carbonyl carbons should be more electrophilic. One thing is here. Second thing, why this halo group is attacking on this carbonyl of acetyloxy group and not that of amide functionality. Here we can compare through this manner that the positive charge on the nitrogen means that the electrophilic you can say electron density is pulled towards this nitrogen. On the other hand, towards this acetyloxy group, here you can see the lone pair of oxygens can resonate towards the carbonyl group. There is resonance, and through this resonance there will be less electrophilic character of this carbon. But in case of amides, there is more less electrophilic character of carbonyl carbon. So therefore this carbonyl carbon of acetyloxy group is attacked by the halo group, and we get the product of removal of acyl halide as a catalyst in this step, and along with the formation of aldehyde and tertiary amide. Here is given the stepwise mechanism with respect to acetic anhydride, and first step is the formation of iminium ion. At first the oxygen with nucleophilic character attacks on the carbon of the acetic anhydride. Here first question is why these nitrogen and oxygen are given positive and negative charges. Then we say that basically this is a coordinate covalent bond between nitrogen and oxygen, in which lone pair of nitrogen is making the coordinate covalent bond with oxygen, and we can show this coordinate covalent bond through an arrow or through a single line along with positive charge on the donor and negative charge on the acceptor. And here, as the lone pair of nitrogen is involved in coordinate covalent bond formation, so lone nucleophilicity of nitrogen is not present here. So only oxygen can act as a nucleophile here, and this acting as a nucleophile attacks on the carbonyl carbon of acetic anhydride, and we get the cleavage of weak bond, that is pi bond, between carbon and oxygen. When this charge moves back and oxygen gets the negative charge, as you can see in the product side. Nitrogen is positively charged due to formation of 4 bonds, and oxygen gets the negative charge due to formation of single bond here. When this negative charge moves back towards the carbon, and here we get the breakage of the carbon oxygen bond, this oxygen is from acetyloxy group, and we get the formation of acetate ion along with the positively charged nitrogen N-acetyloxy derivative. N-acetyloxy because acetyl group is directly attached to the nitrogen. In the next step, the oxynegative charge of acetate ion acting as a nucleophile attacks on the hydrogen that is present at alpha carbon, and the bond, the 2 electrons between this carbon and hydrogen moves towards the nitrogen, making the double bond, and at the same time nitrogen oxygen bond is broken, and we get the acetate ion formation along with the iminium ion formation. The positive charge of iminium ion is counterbalanced by this acetate ion. Here you can ask a question, why this acetate ion is not attacking on the carbonyl carbon of acetyloxy group, which is looking to be more electrophilic as compared to this hydrogen or this alpha carbon, alpha hydrogen. Basically this acetate ion is a conjugate base of acetic acid, which is highly basic in nature, that is, it has high chance for the removal of proton. Number one thing, as compared to its nucleophilic character, it has basic character also. And here in this case the alpha carbon which is attached to nitrogen, which is further attached to oxygen, and nitrogen is also sp3 hybridized with positive charge, so there is much electron with the drying effect of this N oxide group, and you can see the lone pair of oxygen is further resonating towards the carbonyl group of acetyloxy group, and so there is much more acidic character in this alpha proton, and acetate ion easily abstract this proton and we get the double bond between alpha carbon and nitrogen easily, as compared to the nucleophile attack of this acetate ion on the other acetyloxy group. And if you see, if it attacks on that, maybe there are some chances, maybe then we get the previous region from which we have moved here, so there we shall be moved towards the last step. Here after the formation of aminium we move to the second step. Another way of formation of this aminium is through intermolecular. This example was an intramolecular, between the abstraction of proton was by an acetate ion from another molecule, and there was intermolecular interaction and we get aminium ion along with acetate ion. But there are also chances for the intramolecular proton abstraction. Here you can see the acetyloxy group which is attached towards with the nitrogen is stereochemically moved in such a way that the oxygen acting as a nucleophile, oxygen means the oxygen which is double bonded with the carbonyl oxygen of carbonyl group, acting as a nucleophile, attacks on the proton, abstracting it in the form of OH plus, and at the same time carbon hydrogen 2 electrons are moved towards the nitrogen making double bond, and simultaneously nitrogen oxygen bond is broken which is moved towards this carbon oxygen making it carbonyl, and the double bond of initially carbonyl is converted into single bond, and we get the acetic acid as byproduct along with the formation of aminium ion and counter ion of acetate ion. So both are the chances are there, and you can see both moves in the with the similar pattern, both gives the similar type of byproducts, so there are chances of formation through both of these steps. If we compare the feasibility of the interaction, then you can see that there are more chances for the intramolecular as compared to intermolecular, because intermolecular in case of intermolecular interaction they have to come close, then the interaction will start, but in case of intramolecular they are already attached with one of their and there are less gaps between these interacting atoms or interacting species, so there are more chances for the intramolecular interaction and the formation of product is achieved. Second and the last step is the formation of amide and aldehydes from this aminium cation. Here you can see the first step is simply nucleophilic attack of this oxide ion of acetate ion on the alpha carbon, and the carbon nitrogen bond is broken and we get the single bond here, and acetyloxy group is attached on this alpha carbon. And in the product side we get the simple amines, that is the lone pair of nitrogen is now free. This nucleophilic nitrogen attacks on molecule of acetic anhydride on the carbon of acetic anhydride, and we get the negative charge on oxygen. When this negative charge on oxygen moves back towards the carbon, and we get the regaining of carbonyl along with the formation of acetate ion. In this step, if you compare the reactivity present here in this step, nitrogen, the lone pair of nitrogen was acting as a nucleophile on the carbonyl of acetic anhydride. but here are also present the lone pair, two lone pair of simple oxygen, sp3 hybridized oxygen, and also two lone pairs on the sp2 hybridized oxygen. First, if we compare the overall nucleophilicity, you see that nitrogen is more nucleophilic as compared to oxygen, and so nucleophilic attack will be from nitrogen as compared to that of oxygen. Simple sp3, it is a comparison of sp3 hybridized nitrogen and sp3 hybridized oxygen. But if there is present sp2 hybridized oxygen, then due to more S character, the lone pairs are little bit towards the nucleus, and there will be a decrease in nucleophilicity there. So sp3 hybridized oxygen is more nucleophilic in character as compared to sp2 hybridized oxygen. So after the attack of this nitrogen, we move towards the product side, and in which acetate ion is present counterbalancing the positive charge of nitrogen. Here you can see this acetate ion acting as a nucleophile, attacks on the carbonyl of acetyloxy group, and oxygen gets the negative charge, which moves back for the gaining carbonyl carbon oxygen double bond, and at the same time carbon oxygen bond is broken, and we get a double bond between alpha carbon and oxygen of ammonium, or you can see here is the tertiary amide. So there is the removal of acetic anhydride, which was used in the last step, so it is acting as a catalyst here, and we are now with the formation of amide and aldehyde. The R2 group is attached with the carbon, which is converted into carbon double bond oxygen, and when the carbon and alpha carbon nitrogen bond is broken, this R2 group is converted into aldehyde functionality, and at the same time nitrogen after removal of positive charge is converted into simple tertiary amide functionality. Here was the question in the first you can see the products from where this reaction was started, that is the attack of acetyloxy group on the carbonyl carbon of acetyl group, alpha acetyloxy group. Alpha acetyloxy means the acetyloxy group which is attached to the alpha carbon of the nitrogen. And now the same question we have discussed in the case of acylide also, where the halo group also attacked on this carbonyl carbon of acetyloxy group as compared to the alpha carbon and as compared to the carbonyl carbon of amide functionality. If we compare the electrophilic center, as we have discussed there, the electrophilic character is more for these carbonyl as compared to the alpha carbon. Number one thing. Number two, if we compare both of the carbonyl groups, then the acetyloxy carbonyl is looking little bit less electrophilic as compared to amide. Because nitrogen is with positive charge, there is no resonance from the nitrogen towards the carbonyl, so the double bond character or carbonyl electrophilic character of this carbonyl is maintained here. But in case of acetyloxy group, there is resonance from the lone pair of oxygen towards the carbonyl, and there will be a decrease in the electrophilic character of this carbonyl. But the attack is on this carbon. This thing can be explained through the presence of large bulky groups on the nitrogen, which gives some steric hindrance for the attack of these nucleophiles on the carbonyl of amide. So we get here the attack on the acetyloxy group. The formation of product can be in another way. The tertiary amine, alpha acetyloxy tertiary amine, which was obtained in the first step of this slide, can move through the intramolecular cyclization. The above discussed mechanism is intermolecular, and here we can move also through the intramolecular cyclization. In this intramolecular reaction, the nitrogen nucleophilic nucleophile attacks on the carbonyl carbon of alpha acetyloxy group. Oxygen gets the negative charge and we get a 4-membered ring. And as you know, there will be some steric hindrance also, so there will be some although intramolecular interaction has more chances as compared to intermolecular, but here the formation of 4-membered and steric hindered, or you can a ring with some angle strain, there will be less chances for the formation of this 4-membered ring as compared to the above one. And after the formation of this, if there is formation of this 4-membered ring, then the removal of the products is in such a way that oxide ion moves towards the carbon making double bond, and at the same time carbon oxygen bond is broken, which moves toward the alpha carbon and oxygen making is double bond, and R2 group is now attached with the carbonyl. And when the alpha carbon nitrogen bond is broken, we are separated with an aldehyde, and at the same time we have obtained the amide functionality. This is a concerted mechanism in the similar way moves, and if you say there can be a question that when oxygen moves towards this carbon making carbonyl, oxide ion moves towards this carbon making double bond, then carbon oxygen bond is broken. Why not carbon nitrogen? If carbon nitrogen bond is broken, then we are converted back into the reactant, so there will be no progress of the reaction. So therefore we say that it should move from this side so that the product is found, and in actual practice, as we are getting the product, so the movement or breakage will be in this way, not in the that way which moves towards the reactant side. So this is the overall mechanism of formation of amide and aldehydes. So today it is over for today's lecture, and in next lecture we shall discuss about the modifications and general characteristics of this reaction. Okay, thanks.